Today's lecture is what I would say it's the pinnacle, the absolute climax of this course. Okay? We're halfway through exactly, and this is the top of the mountain. But as you know, getting to the top of the mountain requires the last bit of breath. Then it's downhill from there. In a good way. In a good way. As, you know, as a mountaineer. So today we will actually, you got a little test of your concentration and dedication to this course last lecture when we derived the Bernoulli's equation. Yes. Right? Taylor expansions. Wow. Today we will derive the Navier-Stokes equations. Okay? Now, I beg of your complete commitment today because this is going to be hard. It is going to be hard, I'm afraid. I decided it was necessary. It's for your own good. But we won't do it again. I promise that. And this will be the first and only time in this course that we're going to be so thorough and are going to require so much of your mathematical training to be brought forth in this discussion. Okay? That is my promise to you. Yes, but next class, I promise you, we will go back to doing examples, and I will, do my best to revisit whatever it is that requires revisiting in context in the next few classes with some applications. We've done a lot of applications until now, but it is time today to reinforce the mathematical foundations of fluid mechanics. Fluid mechanics is actually a very old topic, you know. The theoretical foundations of fluid mechanics were laid out by Newton. And if you think about it, it's, 200 years of great thinkers contributing to this topic. And as it said in the introduction to this chapter in the book by Post that we've chosen for this class this semester, the mathematics of fluid mechanics is actually considered by many physicists and engineers as the most beautiful, okay? And I know it's hard for you because it's a challenge. You have these mathematical skills yet fresh in your mind, like, I tried to scare you last time with Taylor expansions and so on. Now we're going to take that to the next level. But it is rewarding because this is really, Navier-Stokes equation is really the, all of the details of fluid mechanics are governed by the Navier-Stokes equations. And it's the subject still of a Clay, $1 million prize, Clay, and so on. It is to this day, people dedicate their lives, scientists that are dedicated to research, to this topic. And so it is worthwhile for us to make the effort for one lecture of discussing this in detail. Next class, I promise you, we'll be back to the more, down-to-earth applications that you will feel more comfortable with. Today, I'm going to take you out of your comfort zone. Okay? And so to put this a little bit in context of what we've done before, the analysis that we've done before in terms of control volume analysis, it's extremely useful. But you must have realized that we were continually making simplifications. And it's extremely useful in many engineering applications where we can, in fact, make the assumptions of perhaps steady flow or one-dimensional flow, one inlet, one outlet, uniform velocity and density across all of the control surfaces, and so on. Those assumptions are valid in many engineering situations, and you saw that we could solve a lot of problems within reason, within engineering approximations that normally in a design situation would be covered by a safety factor. You design something, in the end, you're going to apply a safety factor. And so it's okay if there's a 1%, discrepancy or so on. But there are some situations where we want to know all of the details of a flow. Remember the control volume approach, we were able to sort of look at a control volume as a black box. Whatever happened inside, we didn't care about the details, right? What comes in, what goes out, and so on. We apply conservation of mass, conservation of momentum, but there was a black box. We didn't care about the details. There are situations where we want to know the details. For example, if you're designing in the most careful way an airfoil, and you want to be able to optimize that design to reduce drag, a very important subject today in terms of energy conservation is drag reduction for commercial flight. If you want to design this and you want to apply perhaps a computational approach and you want to have equations that will describe the flow at every point in space, at every moment in time, in detail, the only thing to do that is through the Navier-Stokes equations. So, to understand, okay, so let me point out, indeed, that I'm going to lower those lines so that you can see a little better the screen. And let me point out there that the leader of the free world agrees, and he's very happy to have received a T-shirt with the Navier-Stokes equations. I'm sure he uses it for his daily workout. So, without further ado, let's begin. Okay, so to understand the details of the Navier-Stokes equation, what we're going to do is consider an infinitesimally small control volume. Now, what we did before was consider a finite control volume, something that has a size, right? A finite size. For a finite control volume, what we end up really are integral equations. Many times we simplify the integral equations. As you recall, for example, the surface integral could be very much simplified by considering the velocity to be perpendicular to the control surface, the quantities to be uniform across the control surface, and so on. So things come out of the integral, and in the end we have just the area. So, but they are really integral equations. Now, when we look at infinitesimally small control volume, infinitesimal, what we get are differential equations. But the principles are the same. Conservation of mass, conservation of momentum, and conservation of energy. The same principles. But the difference is, in a differential equation, we consider all of the quantities to be functions of space and time. All of the velocity, acceleration, density, and so on, all of the fluid quantities are functions of space and time. Oops, ran out there of space. Now, this is the only way that we could get to the level of detail that perhaps we can write a simulation that will represent this sort of complicated situation, where a high-speed flow hits a bullet-shaped object and produces shock waves. There's a wake behind this object. The shock wave hits some boundaries. The shocks interact with each other, generating yet another source of vortical flow. We say little eddies that move around. The interaction of those little eddies with the shocks produce very complicated patterns. All of this is we wanted to know in every detail what's happening there, and so that we could calculate the point of maximum pressure, how that point of maximum pressure varies in time, and so on. That level of detail will be afforded to us through the differential equations, where each quantity is a function of space and time. So which are those quantities? These quantities are the velocity field. Okay, in the velocity field, by this we mean we've always used this symbol, V vector. But what is this? In 3 dimensions, it's going to be a vector with 3 components, U, V, W, say. We're going to use these letters, U, V, W, for each component of velocity, where each one of these, U, is a function of space, X, Y, Z, and time. V, also the second component of velocity, is a function of x, y, z, and time. W, equally, function of x, y, z, and time. So if you were to want to perhaps study in detail, what is shown here in this picture is actually the details of the flow at an instant in the aorta, the flow of blood in the aorta. And so people indeed are using computational approaches to model this flow and study in detail how does the shear stress change in areas, say, where there's accumulation of cholesterol. How do surgical interventions affect or change the flow in a positive or negative way? These detailed studies, where one requires to know the velocity at every point in space and time so that you could obtain forces, shear stresses, and so on, is what we're talking about. In this little visualization, each little line indicates a vector, so it's a direction, and the length of the line indicates the magnitude of the vector. So the velocity field that we've written here is visualized or represented in a way that we can humanly interpret it, to see that perhaps here there's a recirculation flow. You can see here the velocity is quite large, and so it is here, but in other areas the velocity is smaller in magnitude. So these are the types of things that we want to do: visualize and represent the velocity field in great detail. Similarly, we have as a quantity of space and time the acceleration field. The acceleration field, well, we know the acceleration to be equal to the derivative with respect to time of the velocity. The velocity has three components, and so does acceleration. So we have du dt. This is now a vector where I'm writing the first component, the second component of the vector, and the third component of the acceleration vector. But u, v, and w, we just wrote are functions of space and time. So the total derivative with respect to time involves, basically we have to apply the chain rule. So for each component of acceleration, we need to apply the chain rule. And for example, let's write it for the first one. Du dt is going to be equal to the partial derivative of u with respect to t, plus, now we go with respect to x of u, but x depends on time as well, so we need dx dt. Then with respect to y, equally, I hope that you remember this from your calculus. If not, I do recommend that when you review your lectures, go back and look at whatever source you use, MathWorld or even Wikipedia, for these simple, basic knowledge is pretty good because it summarizes things that you may have not have very orderly notes for, unless you have a really good book. Dy dt. And now with respect to the final independent variable z, but again chain rule, dz dt. So u depends on both x, y, z, the three special components, and time, and therefore the complete total derivative of u with respect to time requires all of these terms. Now we know that this one here, I'm going to change colors here, this one is the u component of velocity, this one is the v component of velocity, and this one is w. These are the velocity components. And we can do the same thing for, so we've done du dt, so we could do similarly, we could do dv dt and dw dt. But I'm not going to write those out because you see it's going to be the same. Now the last three terms, these last three terms over here, you can see that they are u du dx plus v du, we're always working with u, dy plus w du dz. So this addition of three terms is the same as the multiplication of two vectors by the dot product. The vectors being u, v, w, dot product with du dx, du dy, du dz. They want this one here? I haven't written it. It's still there. These guys, I'm just rewriting this part. Just to show you a shorthand way of write this part. So we have the product of these two vectors, where this one, of course, is the velocity, you can see. And this other one is the gradient of the u component of velocity, the same as we did before. For the pressure, we used this differential operator quite a bit when we saw statics, if you recall. And this differential operator, we used this nabla symbol to indicate that is the vector. This u, of course, is here a scalar because it's just the first component of velocity, so it's just a scalar. And this is the vector of partial derivatives. So we can write all of these terms now in quite a simplified fashion in using this, because du dt, now bringing back this term that I was not writing, which was pointed out to me, is the time derivative plus this guy. Everybody with me so far? So you can see I'm going to erase. Everybody got that down? Okay, I'm going to clear this and see that the acceleration field, of course, is these three components, du dt, dv dt, and dw. And so each one of these I can write in the same way. I can write du dt. I've just derived this one, and I'm going to now assume that it's going to be the same for the other components, and you see that this is not a leap of faith, but it's just replacing u by v. I get the second component, dv dt, this is a partial derivative, plus the same total velocity and differential operator gradient applied to v now, and the same applied to w. So the complete acceleration, I can write it in vector form by combining all of these three and writing, of course, if I look at these together as three components, here is the partial derivative with respect to time of the three components of velocity. So I have the partial derivative of the three components there together as a vector. I could write all of the vector terms together. I have the three components of velocity here. So basically, I'm applying v dot nabla as a sort of whole operator to the vector v. Now this here is basically three equations in one for the three components of acceleration. We write here, this is the same as this. We have three components, a vector. Now, we call this term of the acceleration the local acceleration. And we call this term here the convective acceleration. What this means when we look at this and we interpret it is that the acceleration of any fluid particle is composed of two things: the change of the velocity with respect to time, and the change of the velocity of that particle as it moves from an area to another area in a field. The velocity is a field that is changing in space. So basically, if I move from point A to point B, point A has, if you remember that picture of the aorta with all of the vectors represented there, in one instant in time, point A and point B have a different velocity field. So if the particle suddenly would, instantaneously disappear from A and appear in B, the velocity would be different, right? So simply by the fact that it moves from one space to another, the velocity would change. In addition, the velocity changes with respect to time. If the flow was steady, this term would be zero, but this term would still remain. As a particle of fluid is moved from one area to another area of the flow, its velocity will change due to the fact that velocity varies in space. Does that go around your minds more or less? Okay? And this is a very important concept. The fact that there is every quantity in a flow changes because there is flow, because different areas of space have different properties. And so if a tiny little fluid particle suddenly finds itself in another point in space, everything's changed. Velocity, temperature, density, acceleration, forces, everything's changed because every quantity is a field. We call it a field because it depends on every point in space, x, y, and z, and also time. And so there are two contributions to acceleration, is the bottom line of this discussion. One is the unsteady one. Unsteady, this is the unsteady term. And the other one is the convective term due to a particle moving from one region of space to another. Now, because this, you see this, we could look at this ddt plus v dot nabla as being applied to v as an operator. So we could consider ddt plus the vector v dot nabla to be applied as an operator to the whole velocity. Okay? And so this we consider an operator that is actually quite useful, and we call it appears a lot, the combination of this ddt plus v dot nabla applied to something appears quite a bit. For that reason, we give it a particular name. It's called the material derivative. And in the same way as we were discussing for the acceleration, other quantities also change in a flow due to these two aspects, the unsteadiness, and just the fact that moving from one area in space to another will bring us to different properties. Sometimes we write it as capital D dt, and so capital D dt applied to anything is going to be, so anything that we apply this operator to is like doing ddt of that thing plus v dot nabla of that thing, whatever that is. So my little asterisk is a wildcard for whatever we want to apply this to. And it will appear over and over again. It's a differential operator. Good? Okay? Now we're going to do conservation of mass and conservation of momentum. And then it will be all over. Okay? Then you can go back to your next class and think fluid mechanics is going to get easier from now on until the end of the semester. You will feel good about that. I promise you it will be true. I will do all that I can to fulfill that promise. If you only bear with me this class, okay? Sorry? This gradient, nabla? Yeah, okay, so this is just a name for it, for the operator, because see, gradient and divergence are two different things, and because they could be two different things, whether it's applied as a dot product to something or it's applied in the way that we are considering here. Because here the dot product is with the velocity, not with the thing that we have on the right? So because of that, we use nabla as for this, for just that. Yeah, that's all it's. Okay, let's do conservation of mass. So we consider an infinitesimal control volume. That looks like this. It's just a little cube of fluid, and let's call this, so we have our coordinate system here, x, y, z, and so this side is going to be dy, it's very small, dy, dx, and dz. So the volume of this, of course, is dx dy times dz, is just a little cube. And if we recall our conservation of mass for a control volume, we had the change of mass within the control volume is equal, hello? Okay, so conservation of mass for the control volume, a very small little tiny particle of fluid that is actually in the shape of a cube. So what we know is that the change of mass inside that control volume is going to be equal to the difference between what goes in and what goes out. Is this simple concept is still applies. And recall that we were able to write before for the 1D steady case and all so we used to write m dot is equal to rho AV in our previous analysis for control volumes, right? So now we're going to do that, but we're going to look at the fact that every quantity, velocity, this was just the 1D case, right? But now we have three velocities. We have the velocity in the x direction, in the y direction, in the v direction. So flow could be coming in or out from every for each one of those walls. In particular, for example, u comes in here, u say at the point x, and u comes out here at the point x plus dx. So the velocity should be changing in time, in space a little bit, each component. And so we could write, let me just, I haven't been consistent here whether I've used with respect to time or not. Let's just write it as a partial with respect to time of the mass and the control volume. Because this control volume doesn't change, this is going to be simply, the mass itself is going to be, no, let me just write it here. Mass of the control volume is going to be equal to rho dx, dy, dz, because that's the volume. Okay, so let's look at this guy now. We have, let's look at the x direction. We have, like I've drawn here, coming in, rho u, so I'm using this concept, rho u, the velocity in the x direction, and the area of that phase is dx times dz. No, the y. What am I doing? Oh, I've drawn it by mistake pointing left, but in my axis, u actually points in there. So I've made a mistake in my, I haven't been consistent. What did I do? I erased everything. Okay. Let's see if I can do this quickly. So this one was dy, dx, and dz, because we have x, y, z, and therefore u comes in this way, right? U and x would come in this way. We have conservation of mass which was the mass of the control volume equals to the mass going in minus mass going out. And I'm going to write that as for each phase. So rho ux is going into this phase, which is dy dz. Something is coming out the other side. The velocity may have changed. Velocity u now is going to be at the location x plus dx. But the area does not change. It's still dy dz. Now in this direction we have v. So plus whatever comes in the side phase, and that's v at location y times, what's the area there? D, that's the area, right? dx dz. And minus what comes out the other side. What comes out would be v, but v now at the location y plus dy. We've moved dy as we cross that little cube, dx dz. Plus what comes in the bottom and what comes out the top. It's a subscript, yes. It indicates that u is being evaluated at x, or evaluated at x plus dx, because I'm writing it short. Of course, x, u, remember, is a function of x, y, z, and t. But here I've sort of used a shorthand to indicate that u, of course, x, y, and z are still independent variables, but I'm not worrying about that for the time being, because the only thing I care about is the fact that these two are pointing in the same direction, and the only change in u is due to the fact that here I am evaluating at x, and here I am, when I go the other side of the cube, I'm coming out with x plus dx, right? I'm moved in space, so my velocity is changed. Velocity is different at every point in space, and so it's different on this side of the wall than on this side. This is v though. Okay, v, same, moves from the location, so I'm calling this location over there x, y, z, and this location over here would be, I've moved by dy, so would be, this point for example would be x, y plus dy, and z. You see that? Every point is just shifted by dx in the appropriate direction. And this is what I'm using here. So now finally we have possibly something going in the bottom and something going out the top. That's by velocity in the z direction, which is w. So we have w at the point z, and the wall here has area dx dy. That's the bottom area, and the top area are both dx dy. And what comes out the top is the velocity there has changed a little bit, right? Because we moved from the bottom to the top, and the coordinate z goes from z to plus c plus dc, right? We've moved from this to the top. The area is still dx dy. That makes sense to everyone? So that's conservation of mass for that small control volume. We've considered everything that comes in is positive, everything that goes out is negative, because it's on the right side of the equation, and that should be the total change of mass in the control volume, which is, so let's write it, dt of mv, also the mass is rho dx dy dz, because that's the volume. Density times volume equals mass. That's all I've done. So what we can do now is basically divide the whole equation by the volume. Which is dx, dy, dz. For each one of these two terms, the area will cancel out, but I will have one additional one that, for example, if I divide this whole thing by the volume, I will have rho ux minus rho ux plus dx divided by dx, which is the definition. I could apply there the definition of derivative for that particular pair of terms. Does that make sense? Let me just write this. If I have rho, so for example, with the first couple of terms would be rho u at x. So let me be specific here and write it in this way. So you see it's evaluated when you look at it back in your notes. U at x dy dz minus, so these are the first two terms, u at x plus dx dy dz, and I divide the whole thing by the volume, dx dy dz. Then dy dz cancels out, and I'm only left with rho u at x minus rho u at x plus dx divided by dx. So I'm going to say that that is the derivative of u with respect to x over there. So applying the, when I make, of course, dx tend to 0, if dx tends to 0, that is the derivative. That's going to be rho times du dx. You agree? Because it's delta x divided by delta u divided by delta x in that direction, in the limit when dx tends to 0. I'm able to stop and explain it again if you ask me. Yes? Well, rho remains, right? I've left the rho there. So basically I'm using the definition of, I'm using the definition of u at x minus u at x plus dx divided by delta x when the limit of dx tends to 0 is du dx. The definition of derivative. Now, ring a bell? Got you. Okay. Now it's clear. Yes? Clear? Yes, you. You're fine. You're good. Okay. Back there? The ones that are hiding behind the classmates? Yes, question. Thank you. U is a function of x and y and z, but for the moment, just to look at this term, I have not written out explicitly that there is y and z, because this actually is u at x, comma y, comma z, comma t, and this guy is u at x plus dx, comma y, comma z, comma t, and so these are the same. The only one that changes is x. So since I'm only moving in the x direction, I'm sort of forgetting about the other variables for the time being, just to make my life easier and to really see that I can apply the derivative with respect to x here by this definition. And I'm going to do the same with all the other terms, of course, with the other ones. Here for this one, for this pair, when I divide by the volume, dx and dz are going to cancel out, but I'm going to have dy in the denominator. And when I take limit, when dy tends to 0, I'm going to have the derivative of v with respect to y. In this term, this pair here at the bottom, when I divide this pair by the volume, dx dy will cancel, and I will have dz at the denominator. Take the limit when dz tends to 0, and I have the definition of dw dz. So what I want to, let me see, how do I'm just going to erase this. And sorry?
And we were looking at the partial or derivative of mass of this special plan like this. So what happens to the left side of our equation if we divide it into the right side by volume?
We're going to divide by volume.
Yeah.
And the volume of this fluid is very, very small. And we consider it constant. So it comes outside of the derivative. And it's completely cancelled out. And I'm left with d rho dt. Now, let me see. I really have got to use the derivative, the complete derivative here. And I'm sorry about that. I hope that it won't confuse you. But it really is the complete derivative here. Let me show you what needs to be changed, to be clear. This is actually the complete derivative, okay, of the mass with the control volume. So what I really want to have here is d dt. Okay, and I will show you why that makes a difference in a moment. I'm sorry about that. So let me just clear. I want to make sure that you are, following here, and so I will repeat some things. Okay, so I'm going to clear the slides and rewrite some of the things. We have the change of mass in the control volume is equal to what comes in minus what goes out. And we wrote that as rho ux at the point x dy dz minus rho ux plus dx dy dz plus rho v at y and dx dz minus rho v at y plus dy, dx dc, catch me if I make a mistake here, plus rho w at z dx dy minus rho w at z plus dz dx dy. And I'm going to divide by dx dy dz and take limit when dx, dy, and dz tend to 0. On the left, I'm going to have just d rho dt because the volume cancels out. On the right, I'm going to have, there's a minus sign, I think. Yeah, there's a minus sign, right? Whatever it is that I wrote in the previous slide, I probably had the terms swapped. It's u at x plus dx minus u at x divided by dx. I don't know if I wrote it that way or not, but it should be, just to remind you, u at x plus dx. I don't know if I wrote it this way, I just want to make sure. U at x divided by dx, limit when dx tends to 0 is the definition of derivative. Yet here we have them upside, the other way around. This is the at x plus dx, and this one is at x. So there's a minus sign. Minus rho du dx plus, they should all be minus, rho dv dy and rho dz, sorry, the w dz. Okay, so now we can see that if the flow is incompressible and rho is equal to constant, then we get that the derivative of 0, so I can divide by that, and we just get du dx plus dv dy plus dw dz equals 0. Now this derivation that I'm following is the same one that appears in the book by Post, but the one for the conservation of momentum that we're going to do is going to be different. And notice here that this is the same as writing that the divergence of velocity is equal to 0. So basically the continuity equation or conservation of mass for the case of constant density is very simple. It ends up being, this is continuity for constant density flow. But in general, we need, we'll take a break after this. In general, we have d rho dt equals 2 minus, what do we have here? Rho minus rho, and I also can use this operator there. And I'm going to also note that this is the total derivative of density with respect to time. So d rho dt, in rho, since rho is a variable of space and time, I would have to apply also the chain rule and write d rho dt as, so this guy is d rho dt partial plus d rho dx times dx dt, chain rule, plus d rho dy dt, chain rule again, and finally d rho dz dz dt. And as we've seen before, what appears here is u, v, and w. Again, they're moving all the chairs in the floor in the room above us. Good so far? So what we're going to do is notice that here on the right-hand side we have this right-hand side. Right-hand side is equal to, we have the partial with respect to time of rho, and here we have velocity dot nabla, this operator applied to rho. We have the rho dx, the rho dy, the rho dz. On the left-hand side, we had this left-hand side minus rho. Of course, these two things are equal, minus rho. So these two things are equal. Okay? Now, these two I can combine. I basically remember the minus sign, so I'm going to bring it to the other side, and I'm going to combine them as a derivative of a product. So I have, finally, this is my final equation, but for the most general case of the density for compressible flows. Let me just write it out, and I'll clarify any doubts immediately. And here, remember this nabla, this little triangle here, is a differential operator. This differential operator now is being applied to a product of two functions, and so it's nabla of rho with v constant, and nabla of v with rho constant, which is these two terms that I'm here. So the product rule has been applied backwards. Okay, you have a question?
Yeah, just when you were writing on the left-hand side, that's not after the v, up top you wrote minus rho.
I have some sort of weird term.
Yeah, I
things
assumed
that,
that was like prime.
no. Sorry, it's this is a vector here. This is v dot from here. This is just that. Sorry, This is the most general case for continuity equation. This is a continuity equation for compressible flows. And for the most general one of the density can change in space and time. Conservation of mass. The one on Obama's T-shirt is this one. You want to see it again? He has conservation of mass first, and then conservation of momentum. Okay, we'll take a break immediately, but let me show you Obama's T-shirt. And you can make it out just barely there. See? Conservation of mass for an incompressible. So his T-shirt is for only incompressible flows, okay? It's not the most general case. Okay, let's take a little break. I think you need it.